So, pellets have low angle of repose, therefore, the layer formation is flatter than other material in the furnace. Control of layer thickness, coarse particle at the center or at the wall, corrective measure of the gas flow change in burden etc. can be performed either by double well or well-less charging devices, which are shown below. These few devices in the starting of our introduction I shown you, but now I will show only these two which are mostly used in a blast furnace plant. So, this is double well charging and this is well-less. So, you can see in double well charging you have a very limited, so charge is reflected through this armor plate and there is a limited only movement by which you can do that, and even sometime by pushing a rod here also you do that. So, it gives a less flexibility in changing the pattern or in distributing the charge. However, in the well-less one is through a chuit which can rotate in all the direction and it has a much more maneuverability in distribution or feeding charging the material. So, it can come up to here. So, in most of the modern blast furnaces or the coming up blast furnaces, this is being adopted, the well-less charging than this, but most of the furnaces are having this, but the very new furnaces are having now well-less charging, because that gives the more flexibility in controlling the burden distribution. And now you are already aware about it, how the burden distribution can control the gas flow, and not only the gas flow, in this gas flow in turns control the heat transfer and mass transfer, which is very important. So, these are the things which are very important in terms of distribution of the burden charge. So, well-less charging has wider flexibility in controlling and distributing the charge inside than the double well charging as depicted in the previous figure. So, in well-less charging with the help of chuit, one can have a wide variety of charging and can vary the impact point of the charge in a more versatile manner and less segregation you have. So, segregation means your smaller side and bigger size particle, even density, based on the density difference, the segregation can occur at the point of impact when you are putting the material, then segregation can occur. There are many things in fact in the charging which one has to consider. Mostly at the impact point you will find the fine deposition comes, we will show that. So, in modern blast furnace double well charging is equipped with movable armor which gives more flexibility in charge distribution, but they are still not as versatile as the latest well-less charging devices. So, when pellet 12 millimeter diameter or sinter 25 millimeter diameter are charged over coke layer, which is about 45 millimeter diameter, a mixed layer is formed at the interface, which can hinder the smooth flow of gas and may give the circumferential flow. As you know, this is a big particle on which you are charging, let us say this is smaller, as I said, 4 times difference. So, between the voids these pellets can settle between the coke voids, and that will reduce the permeability, especially at the interface. And when this happen at the interface, then the more resistance to the gas flow, and then there is a preferential circumferential flow in that. So, central and valve flow can be kept to their optimum value by adjusting the charge distribution at the top. The flow is mostly controlled by coke to ore ratio. So, usually 70 centimeter thick ore layer consumes about 25 centimeter thick coke layer. So, you can then imagine the resistance offered by the ore layer. So, at the throat the coke layer thickness is about 45 to 50 centimeter, and when it reaches to the valley region where the diameter is about 1.5 times higher than the throat region, the coke layer becomes thin and surface area becomes quite high. This we discuss in terms of repose angle also, layering charging that as you go down it becomes much flatter, and then of course also thinner, because same volume is spreading in the higher area. So, at the valley region the thickness of the coke layer should not be less than 20 centimeter for a smooth operation of the furnace. With the when you are saying a 20 centimeter, and you know already the charging is about charging size of the coke is about 45 millimeter to 50 millimeter, which is about let us say 5 centimeter. So, you are talking about 3 to 4 layer of the coke, which is quite thin in that way. So, one should keep at least about 20 centimeter for the proper permeability and the smooth operation of the furnace. So, with the PCI operation some adjustment have to be made in this ratio to keep running the furnace in a smooth way. So, with the PCI operation actually your coke consumption reduces, but you cannot compromise really with the minimum thickness of the layer near the boss region or lower part of the blast furnace. So, some sort of compromise has to be made. So, a smooth operation of the furnace occur in that. So, it is proposed to have the coke layer thickness at least 3 times the coke diameter in case of maximum injection of pulverized coal. So, ore layer should have optimum thickness as reduction potential of the gas decreases faster in the ore layer. So, thicker ore layer may not reduce properly and will be difficult to melt in the lower region of the furnace. Schematically it is shown in the next figure. So, even for that one you need a optimum thickness of the ore and coke layer should be maintained. So, this shows about the ore layer thickness. So, normal 100% thick, and if you are increasing the thickness, essentially what is happening at the center of it is not getting reduced properly, and this travels down, and then this reduction will occur in the lower part of the furnace where the direct reduction and then more heat would be consumed endothermic, and as we discussed the chilling and other effect can come into the picture, and operation may not be a smooth one. And also it should be a proper descent from top to bottom. If you do not have a proper descent of the material, again you have a maldistribution of the gases. One possibility is shown here, where if this coke layer thickness decreases, what will happen? The ore layer will, or a smaller particle will penetrate into that, more void fraction will penetrate into that, and that will stop or will give more resistance to the gas, and the pressure drop will increase. Again the smooth function of the blast furnace will disturb. So, one has to once the aim should be the thickness layer should be maintained even in the descent, and it should not become in an erratic way. So, in formation of mixed layer, So, when actually you are charging the material say on the top of the coke layer, you are charging the sinter. So, at naturally at the impact point, this coke will displace, which you have seen in the previous one, and during the charging of the sinter and coke is at the bottom, you will see previous profile of the coke layer was this. After charging the sinter, it became like this. When it will come over here, you will get a mixed layer of the sinter and the coke. So, this portion in one way really giving more resistance to the gas flow, because your void fraction has decreased in this. If because let us say if it is pellet, the void fraction is 0.41, and for coke void fraction is 0.51. So, certainly pellet will settle down within the void, and that will create or give rise to the gas resistance to the gas flow. So, these are few situations which may arise in the charging, and one should avoid and take proper care of these things, because this will lead to the maldistribution of the gas flow and eventually then your reduction and heat transfer. Okay, so, one example based on this is given here. So, a blast furnace is producing 10,000 ton hot metal per day. If total coke consumption is 350 kg per ton of hot metal, then what would be the coke layer thickness if one layer of iron ore, and you can assume iron ore as a pure hematite, contains 63 tons of ore. So, when you are charging a one layer, that is containing about 63 tons of ore. What would be the iron ore layer thickness? If 50% ore is reduced by direct reduction, estimate the thickness of the coke layer in valley region. So, 50% you assume it is reduced by direct reduction, then what would be the thickness in the valley region? Assume that iron ore hematite is directly reducing to iron in valley region. Stack and valley regions diameters are 8 and 12 meter respectively. The density of ore and coke may be taken as 5000 and 800 kg per meter cube respectively. So, here you have to find out the coke layer thickness and your ore layer thickness in the valley region and even the stack region. So, how would you do? Now, assumption is already said your ore is hematite, it is a pure hematite. So, under that condition 2 moles of iron are produced from 1 mole of ore. So, hematite Fe2O3. So, 1 mole of ore will give you 2 moles of iron. So, in terms of tonnage, so 1 ton of iron would need a normal stoichiometry way, you can calculate it. So, it will give you 1.43 tons of ore. So, 160 is the weight of the hematite and 2 moles 112 is for iron, and you are going for a 1 ton. So, you need 1.43 tons of ore. Therefore, coke needed to reduce 63 ton iron ore, because in one layer it is given 63 tons iron ore is there, and we know now so many tons of ore is needed for 2 moles of iron, and it is also given for to reduce this you need 350 kg per ton of coke is needed per ton of hot metal, and for 63 ton, and with this you can know how much coke is needed to reduce 63 ton. So, 15.4 tons of coke is needed. Now, you know the amount for the coke also. You can assume the cylindrical stack region, then you can easily find out the thickness of the layer by a normal volume, knowing the volume of the one layer of the coke. So, density of the coke into the volume of one layer of coke equal to the weight of one layer of coke. So, weight of one layer coke we already found it 15.4 ton, and we know already the diameter of the stack region. So, and the volume of that would be the pi r square L. L is nothing, it is the thickness of the coke layer. So, if you equate that one, you get the coke layer thickness about 38 centimeter. And similarly, you can find out the thickness of the ore layer, which would be about 25 centimeter, and this is actually in the stack region. And so, in stack region the radius is 4 meter, and that is how this is coming here. Now, 50% ore is reduced by direct reduction, that is in the belly region. So, which means 63 ton we are putting. So, 50% of it 31.5 tons ore is reduced by direct reduction. So, and it is also given the direct reduction is mostly you can consider is from hematite directly to iron. So, we can write this reaction. So, according to this, you to reduce 160 kg ore you need about 36 kg coke. So, reducing 31 ton ore you will need about 4.25 tons of coke. And now again you can calculate the volume of that and equate with this tons of coke, you can get the value of the coke layer thickness in the belly region, which comes about 7.1 centimeter thickness in the belly region of the blast furnace. So, that gives you some idea how you can calculate based on the reaction and other parameter which is given the layer of the material in different region, and can try to maintain it. This figure shows the change in viscosity of the mixture with temperature, and this can have a major influence in the softening melting zone in the smooth operation. So, as we said, the gas flow is very important. Now, we are coming to the cohesive zone, and the cohesive zone which you know we had discussed few times, and it is shown in the starting actually in this figure, where we are having a inverted B type or W type. So, this is the cohesive zone where the ore especially is in semi fluid state. So, like a mushy zone what we call it. So, this brown one is becoming fused. So, when it becomes fused, which means the gas cannot flow through that. Already ore has a very low Boyd fraction. So, gas already feels quite a big resistance, and now in this condition where it has fused, the gas cannot flow through that. So, reduction of course becomes a problem, and not only the reduction, main thing how to gas has to flow. So, that is the reason you have to maintain this layer thickness of the coke. If it get disturbed, then gas cannot flow from here, because this is the only material which is solid now and has also voidage, a good amount of voidage, about 50% or 0.51 as you have seen it. So, most of the gases, they are passing through this coke slit now. So, so this zone is very important to maintain the viscosity, the melting point, softening melting point, and we are talking about that. In fact, we talked a little bit about this zone before also in the materials property, that materials softening melting temperature should be as high as possible. So, this zone should reach more downward side, and also softening and melting, these are two things. It should be narrow. The softening is at which it becomes a fusion becomes, or the it start a bit melting or liquid temperature, and melting is at which it becomes totally in the liquid form. So, that range of softening and melting should be narrow. So, in that way the cohesive zone thickness would be narrow, and which means you can reduce the resistance of the gas, or gas will have a less resistance than the wider this cohesive zone. So, this figure shows that how this viscosity is changing with the temperature for the mixture. So, for hematite at the high lower temperature, viscosity is quite high, even for magnetite is quite high. For wustite it is still high, but not that much. But if you look at the slag formation, that viscosity is really low. So, that can easily flow, and what you need it, you need also quite a good viscosity in that one. So, as soon as its fusion occurs, materials should flow through the coke voids and will offer less resistance to the gas. So, high temperature properties of the materials are also very important. Now, this figure shows some of the phenomena. I think we talked a little bit about the slipping or hanging. We talked in terms of when the forces upward forces are greater than the downward forces, the material will not descend, hanging may occur, and we said few causes of it. Also sometime happens bridge formation occurs, and that occurs more near the fusion point, the particle are getting fused or something. So, arc formation occurs, and when arc formation occurs, the below it is mostly the void, and it keep on building, and the void also keep on increasing. As you can see in this figure, this is more as a schematic way, the figure which is showing. So, and on here in one way the arc is forming and it keeps on building, and that situation deteriorate, and once this become bigger and material weight keep on increasing, suddenly it falls, and that is called slipping, and that is disturb the whole thing. In the next figure you will see what may happen. Due to the slipping, the layer structure get disturbed, and once the layer structure get disturbed, you have a very big problem with the gas flow. Gas is feeling more resistance, like in this one the layer structure has gone this, now gas has to travel not only the longer part, even the resistance it has to face through that, and which means the high pressure drop, and operation of this will get disturbed, it will not run smoothly, and then you have to change again the layer structure from the starting itself. And so, this only can be corrected by putting again proper layering at the top. And when once you put it at the top, to reach up to here, it may take 8 to 10 hours. So, your really furnace, or at least for 8 to 10 hours, is not going to run in a smooth way. All the chemistry of the slag and metal will get disturbed, production will get disturbed, everything, and it takes quite a lot time to bring it the furnace to the normal operation. So, this sort of disruption can occur, and one has to avoid that. So, when either the void or weight of the material above it becomes too weak, the bridge collapses and the furnace slips, which disrupt the layer sequence and further deteriorate the gas flow and hence the furnace operation. This can be corrected by establishing the proper charging sequence, which can take 6 to 10 hours, as I said. So, really quite a loss in the production and the efficiency of the process, and sometimes this may result in slugging or channeling occurring when the gas flow is not uniformly distributed, but follow a preferred path through the bed. So, it can even go to the channeling mode, where the gas is flowing through a least resistant path in a one preferred direction. Then you are not able to utilize the proper reduction potential of the gas and heat transfer capability. Slugging also occurs mostly in this sort of region, that this actually phenomena is also can be known as slugging, where this gas has to bubble through. So, it goes up the whole material, taken away, and then it collects. So, that sort of slugging can occur, and which is again is not good for the smooth running of the furnace. This figure shows the size distribution at various locations within the blast furnace and corresponding empty tube fluidization velocity for various material. So, if you look at this, because this is radius of the furnace versus mean size, and the upper layer, middle layer, lower and mixed layer. So, lower layer, when you say this is belonging to the lower part of the furnace, and the middle section in the upper section. So, obviously, in the upper section you are charging it. So, mean size would be higher, which you can see from this topmost curve. So, this is high, but as you layer goes down, a reduction other thing takes place. So, their size decreases, and of course, at the bottom one size decreases further. So, you can also think that permeability also decreases, and this shows for the mixed layer, this one which is coinciding more with that. And if you look at the respective this in terms of density, so you have typical density of iron ore around 5. So, that fluidization velocity for that with respect to the particle diameter, you can see in meter per second. So, usually we saw about 20 millimeter or particle diameter. So, to fluidize you need about 10 meter per second. On the other hand, coke is coming sort of in this range. So, where you have the fluidization velocity, again the size is this. So, you have about 6, 7, and then you have for sinter and other. So, this gives some idea for the different density of the material, what would be the fluidization velocity. So, furnace should operate below that limit, and that is one of the reason that you cannot have a very small particle of coke, otherwise they will get fluidized here. And these are also at 2 temperature it is given. So, as the temperature actually increases, you can see seems the fluidization, because the gas density becomes lighter. So, you need a higher fluidization velocity for the fluidize the same diameter particle than at the lower temperature.